Alright, this is Stinson's class. So, hi again, Mr. Tressel here. Today's assignment, alright, talk about that. So, you might see it in hard copy, meaning like an actual piece of paper, or you might see it online. Directions, alright, so today's date says, copy the details in this assignment into your notes as you go through the assignment. Use your notes, answer the questions, watch the videos that go with it. So this assignment has some information, and as you go through the information, write it down. Okay, it's how you learn. It's called kinesthetic sense. Kind of like when you were writing your name, your phone number, or your parents' name. You commit it to memory. So by writing it, it helps it stick. So write down, the information in your notes, and then when you see a question, use your notes to answer the question. All right. The video. Okay, so I'm going to use an older video. Actually, I have long hair in this video. And in the video, I touch on a couple of topics that we're learning about. So you're learning about waves, right? And you know that there are parts to the wave. The top of the wave is called the crest. The bottom of the wave is called the trough. The measure from the crest to crest is called the wavelength, or the measure from the trough to trough is also the wavelength. You've learned about frequency, okay? You learned about hertz. You've learned that waves carry energy. So in the video, I touch on mechanical waves a tad. So that's probably going back for you a little bit, mechanical waves. While I'm talking right now, you're not in this room, but there's a microphone connected to the camera, which is 5 feet away or so. And so my larynx is vibrating, my voice box, and the vibrations that my larynx is producing is being transferred from where I am to where the microphone is. And if you were in this room, it'd be to where you are. So the gases in this room serve as what they call the medium. All right. So mechanical waves need a medium to transfer their energy. All right. Now a medium could be a solid, a liquid, or a gas. In this case, right now, it's the gas. But have you ever gone underwater, maybe while you were swimming, and heard noises and hear how loud they are? More loud than when you're not in the water. So when you're underwater, a liquid, the mechanical waves, sound waves, travel further and more powerful, let's say, than opposed to out of liquid and in the gas. Whereas they travel even further through a solid. So mechanical waves need a medium, right? And the medium can be a solid, a liquid, or a gas, right? In the video, I bring a guitar in and we talk about amplifying a sound. And when I say amplifying, it's raising the amplitude. So back to the parts of a wave, you got the top, the bottom, the crest, and the trough. Well, the amplitude is the height of the wave. How much energy, how tall it is, how much energy is it? How much more power does it have in terms of height? Okay. So in terms of power, though, just to back up, the wavelength, the longer the wavelength, the less power it has. The shorter the wavelength, the more power it has. It's because more energy, more of the wave can pass through a given space. The frequency is greater when the wavelengths are shorter. All right, so long wavelengths, like radio waves, going to shorter wavelengths all the way to gamma waves. So in the video, let's see, might be 2 videos that I'll do, kind of stitch them together. It'll look like one for you, but it's technically 2. Ever play with glow sticks before? You snap them, shake them up, and they glow. Usually they're green, but nowadays they have all these different colors. There's a story that I'll tell you briefly. A person of history. This was a mathematician, all right, and he. All right, so let me back up. So Sir Isaac Newton, all right, Sir Isaac Newton was somebody who's done many things and is an accomplished scientist, mathematician. But this person, Sir Isaac Newton, he demonstrated that the white light found in sunlight actually contains within it all the colors of the rainbow. And what he did, if you know what a prism is, usually made of glass or crystal, they got certain cuts to them which make the light come in and reflect. They're kind of pretty, or like a diamond ring, prism. So what Sir Isaac Newton did was he took sunlight, okay, streaming in sunlight from our sun, and he let that sunlight pass through a prism, which gave it the colors of the rainbow. Okay, then he took another prism and he aimed it, you know, he calibrated it as such to take that white sunlight that was split apart from the first prism into red, orange, yellow, green, blue, indigo, violet. So he put the second prism to collect the red, orange, yellow, green, indigo, violet again, and then basically create white light from that. So what he did, just to put perspective on it, is he took the sun's white light, split it apart into the colors of the rainbow, and then combined it again with a second prism back to white light. So he essentially confirmed that within the, you know, white light that comes from our sun are all the colors of the rainbow, right? When I was a kid, we were talking about televisions. This is kind of going, you know, back to that. So you saw a video yesterday where I had the little small TV. Well, when I was a kid, big screen TVs, you know, TVs that were larger than normal, were projectors. And you might look in your room and see a projector mounted to the ceiling. Well, when I was a kid, the projector TVs, they had the colors, so whatever was on the TV, the station, whatever you were watching, was passed through these tubes, and the colors were red, green, and blue. Right? So it was just kind of like an odd thing when you're a kid and you're looking at the screen, and it's, you know, it's all the colors, you know, it's every white and black and yellow and everything that you can think of while you're watching the TV. But where that image was being projected from, when you looked at it, it was actually three separate tubes. One was red, one was blue, one was green. And when you looked at it, it was the image of whatever you were watching all in red, or the other one was all in green, or the other one was all in blue. But when they were combined together, you know, it gave you every color that, you know, you're used to seeing when you're watching television. So that kind of stuck with me. So in the video, that has to do with light. So when you're talking about the primary colors, red, green, and blue, they combine together to form white light. So in the video that I'm going to show you, let's say, do like this. The video that I show you now, white light as an example of that the spectrum of light of white light composes of red, green, and blue. So there we go. By mixing red, blue, and green glow sticks together, the chemical, you get this white light as an example of that the spectrum of light of white light composes of red, green, and blue. So there we go. I mixed white. All right, you just watched that video where I took the glow sticks, I cut out I removed the chemical luciphase, and I combined red, blue, and green, creating white light. So I demonstrated that within the light spectrum, the visible light spectrum, you can create white light by combining red, blue, and green. Okay, pretty cool. So now here's another one. Everyone, this is a full class, 6th period. Today is Thursday, the 17th. So today's lab goes into a couple of things. One, we're going to review a little bit of wave and what parts of waves and how that might, you know, apply to something that you're probably familiar with. The other thing is color. All right, so color. We've already had a lab that was based on glow stick solutions that were mixed together, the visible light spectrum of the color white. So what we did is we took glow sticks, the colors red, blue, and green, cut open the glow sticks, and then we took the glowing chemicals and mixed those colors together, red, blue, and green, creating white light. All right, so that's one aspect of light, visible white light, and the primary colors of white light, red, red, blue, and green. So we're going to do pigments now, the primary colors of pigments. Now pigments can be like anything that has color to it has pigmentation. So my shirt, a plant, your hair, your skin, all of that. Pigmentation. All right, so let's use my shirt. This is red, okay? So the color red. The color red we see because this material is
is made to be the color red because of a dye that it's used, the dye that the threads are, you know, exposed to, making the material appear to be the color red. Why is it red? Because it is absorbing all the colors of light in the spectrum except the color red. It's reflecting red. So it's basically like a rule of thumb. Whatever color it is, that's the color it's reflecting. It's absorbing all the others. So here is the example. Ever played with paint? I know I did. I used to put my hands on it and then all over the walls and even the ceilings if I could reach it. I got in a lot of trouble. Didn't I, Mom? All right. So the color blue, all right? The color green, the color red, all right? So we've got these three colors. Let's put this around. Here's our colors. Let us, when I say us, I mean me. Let me mix these colors. So you see the color green or blue or red because it's reflecting that color and absorbing all the others. So as we start to mix these colors around, if you ever play with paint, you know, yellow and blue make green and white and red make pink and yellow and red make orange. You can, you know, make all these different colors. If you mix these three colors, because they're primary pigment colors, you start to get this color. It looks a lot like black, and if you keep going, it becomes the blackest black, jet black. I'm gonna use my other hand because I can't mix it that fast. All right, so here we go. Mixing it. Goes to a dark gray. And if I kept mixing this would become jet black. But for the sake of time, it's getting pretty black right now. For the sake of time, we're gonna stop there. Now the next thing, that's one component of today's lab. The next thing is gonna be the parts of a wave, okay? So the parts of a wave, we remember the tops are called the crests and the bottom is called the trough, and the distance from crest to crest is wavelength, or the distance from trough to trough is wavelength. Again, you guys can't see this right now, but I'm gonna give you the video. So, try to pay attention. The distance between these crests is the wavelength. That means that the frequency, how many peaks pass through a given spot. Yep. Yeah, she's, sorry. Sorry, I didn't know what she was doing. Just watch yourself with the camera, the cord, because it's going to shake the screen. Okay, sorry. So let's pretend that amplitude, all right? So the other part of a wave is the amplitude, the height of the wave, how much energy it carries. As more energy is increased to this wave, the higher the amplitude gets. So let's just say that we take this crest right here and we raise it up to right here. That means the amplitude goes from here all the way up to here, okay? We do the same over here. We take it, we raise this crest all the way up to here. So now the wavelength, which is this distance, is the same now, but it's just higher up. So it went up to here, went up to here. It's just higher across, or it's the same across, it's just higher up. That means there's more energy in this wave. If you've ever had a car stereo amplifier, your brother, your sister, maybe your dad, or maybe your mom, they amplify a signal. They amplify a sound wave. They increase the amplitude. So an amplifier amplifies the amplitude of a wave, a sound wave. A lot of ways you can think about this is your phone. You know, your phone, you turn it up as high as it'll go as far as volume goes, and you reach this kind of, maximum. It doesn't let you go it doesn't become any louder. And they pair the phone, the speaker is paired with the amount of, the amplitude of the sound wave, so that way it doesn't distort it. But it's one way to think about that. If you've got a phone that's creating a signal, it's playing music, but then you plug it in. Maybe you've done it, Bluetooth, connect it wirelessly to a stereo. It gets louder, right? Okay, so that's one way. Can I get you to scoot over just a little bit? Because I'm going to put the camera right here. All right, so I'm going to put this camera right here.
On Adapted Mind Reading, stories are designed to build vocabulary and comprehension. There are...
Carefully and gently. All right, scooch that. Okay, here we go. An example of increasing a sound wave, which is a mechanical wave, would be, I've seen this before, guitar, which by the way, I have another one coming on Christmas. Yes, that is 1 week and just hours away. Can't wait. Okay, so I'm going to plug this in, turn it on, put on my little show for you, an example of how one small sound wave can become the same, it's exactly the same, Actually, let me do it like this. Sorry. This is the best way to do this. So I'm going to come here. It's not plugged in. It's not electrified. Okay, so this is an electric guitar. They have an acoustic guitar that doesn't use, the electric side to it. But let's just pay attention to this. So when I play this, everybody quiet. Shh, 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 shh. When I play this. Sounds great, but it's not that loud. Okay. So I'm about, 2.5 feet from where the camera is to where the guitar is. So there again, sound wave is being transferred, the energy when I strum this. Everybody hear that? This is the E, A, D, G, B, and then high E, okay? When I strum these, the energy is being carried from the gases in this room to the microphone and that camera. So this particular one has a pickup to it. So electric guitars, they have a pickup. Some of them have like 3. This one just has 1 because it's the only one I wanted. It picks up the vibration and then transfers it into a signal, and then there's circuitry in here that go to this jack. So I'm going to go plug this jack into an outlet. Okay. So we're going to compare what you just heard with what you hear now. That's the deal. Alright. I'll play the same riff that I just played there. Okay. Alright, so anyway, that's cool. Alright, that's cool to be able to do that and to be able to understand what's happening. Now you understand a little bit. A sound wave can go from, basically this. I mean, literally, listen, now that it's off. Okay, so you can hear it. It's the same. It's just louder and it's cooler.
All right. So you just watched primary pigments. Okay, so primary pigments has to do with mixing the colors together, which you just saw in the video, which were pigments, and the pigments give us the color that they are because they are reflecting the color that we perceive them to be. So let me say that again. If you see the color red, all right, for example, it could be any color, but let's just choose red. If you see the color red, it's because the pigments are absorbing all the colors of the rainbow except for the color red. It's reflecting that color, that pigment, red. All right. If you see the color yellow, it's absorbing all the colors of the rainbow except for the color yellow. So that goes with any color. If you see the color black, it's because the pigment is absorbing all the colors, of the rainbow. All right. So when you saw the mixing of the paint, it combined together, pigments combined together, the primary colors to form black. Okay. So now, when you watched the guitar demonstration, you saw that a signal, a sound, was amplified. The amplitude was increased, giving it, a louder sound. So it's the same shape wave, just giving it more height, higher amplitude. Okay. Let's go back to yesterday. We were talking about waves on the electromagnetic spectrum. radar, more specifically. So radar, going back to World War and, you know, things that are used for war, radar was in something that was brought out of necessity to check to see what kind of objects were coming into our airspace, you know. And it later became something that is used in commercial airlines, so that way airports can keep track of where their planes are, and incoming planes, outgoing planes, and you can, you know, get a sense of, you know, where they are, and you can give the pilots guidance on where to go so they can avoid, you know, air collisions. But when it comes to war, and it comes to an enemy that is trying to invade the airspace of your country, you want to be very sure if somebody's, you know, coming in to do harm, so that there's an aircraft coming in to do harm. So there's been development, going back to military development, things that are brought out of necessity, to try to come up with a paint that is applied to the aircraft to absorb the radar. All right, so let's talk in picture. The radar is sending out waves. All right, so I don't know if you've ever seen the rotating dish, and they send out waves. So when that dish rotates, it's sending out a wave. It's hitting an object out in space. That wave is bouncing back, and there's an instrument that collects that wave. Let me put a pin in that. Have you ever maybe seen a police officer with a radar gun? Maybe you've been in your parents' car, radar gun. It's an officer who's trying to catch people speeding. Sort of the same principle. The radar gun is sending out a signal. That signal is hitting an object like a car. The signal bounces off the car and comes back to the original source, and then there's basically software that calculates how long it took for that signal to be projected out and to come back, and it can calculate the distance traveled, how fast something is going. All right, so radar is used for determining where something is and where it's going and how fast it's moving. So going back to what I said with putting a coating of paint on a airplane, that's meant to avoid being detected by radar. So the radar is sending out a signal, but this special type of paint is not letting the radar signal be reflected back to the original source to where it can be detected. It's actually absorbing the paint. Not absorbing the paint. It's absorbing the radar signal. So the paint is absorbing the radar signal. So what that does is essentially it leaves the object undetected. So the radar source is sending out signals. It's not getting what you call a return. All right. So it's stealth. And so in that regard, this is something that would definitely have an application for, you know, military use. So we, going back to a species, you know, we have borders and countries, and these countries have their own laws and rules and regulations, and sometimes countries, as you know right now, are in you know, war with each other. And so when it comes to protecting your country, you know, you need to have these types of you know, technologies available. So going back to us being a species, saying, all right, well, how can we use these naturally occurring, you know, things that are natural in the world, like we were talking about, these waves, how can we use that to our advantage? Well, in this case, radar has become a very normal, you know, it's a widely used system all over the world. Air traffic is controlled by radar. Well, when you're trying to, you know, avoid detection, there you go. So let us say that we want to, for the most part, and this is going off of my class, okay, so if you are honors, you should be testing out, have already tested out of, but you know, if you haven't, you need to be tested out of this unit fairly quickly and get into dynamic Earth. No, sorry, I said that wrong. Back up. If you are honors, you test out of this unit and you get into properties of matter. That's what it is, properties of matter. If you are not honors, you test out of this unit and you get into dynamic Earth. Okay, so we need to make a goal for that. But today, that's your assignment. So you'll do that, and have a great day.